Okay, so in this video, we're going to talk about particular Fourier transform pairs between these two functions. One of them is the Rect function, which you know about, and the other one is the Sinc function, S-I-N-C, it's pronounced Sinc, which we're going to talk about today. So we're going to look at Rect and Sinc Fourier transform pairs. And these transform pairs turn up a lot in ECE 45, so it's a good thing we're looking at them. Okay, so what is that sinc function? So the sinc function, okay, S-I-N-C, is what? Well, I'll define it. The sinc of t is one of two things. It's almost all the time, it's just sine of t over t. Okay, that's if t is not equal to 0. You can see we don't want to divide by 0. And so if t equals 0, what we do is we just put in the point that would make this function continuous. And you can either graph this or you can use L'Hopital. You know, this is as t goes to 0. Sorry, t equals 0. As t goes to 0, this is going to 0, this is going to 0. So L'Hopital, we can take the derivative of the top, we get cosine of t over the derivative of the bottom 1. And as t goes to 0 there, cosine of t goes to 1. Okay, and that's what we filled in with. Okay, so that 1 is just to make it continuous. And you'll see when I draw it that it makes sense that should be 1. Here's what it looks like. Okay, so that is the sinc function. And right there is that 1. Okay, this is 0. And then all of these 0 crossings on the t-axis, and it goes forever and ever. I'm just not drawing it forever and ever. I'm just drawing it here. The 0 crossings on the t-axis are just when the sine function equals 0. And we know when those happen. Those happen at pi, 2 pi, 3 pi, and so on. Negative pi, negative 2 pi, negative 3 pi, and so on. Okay, so that's the sinc function. And one thing to note is that I've drawn it symmetrical about the vertical axis, and it turns out it really is. Okay, so sinc is an even function. Okay, what does that mean? That means that when I flip it across the vertical axis, it looks the same. In other words, when I plug in negative t, I should get sinc of t, which I do. So I get sine of negative t over negative t, negative sine of t over negative t, the negatives cancel. I get sine of t over t, and finally sinc of t. Okay, so this shows that sinc is an even function, and so it is symmetric across that vertical axis. All right, so now what's the point of defining this function? Well, it turns out it comes up as in Fourier transforms. So what we're going to do is let's find the Fourier transform of f of t, which is going to be rect of t divided by some constant t naught. Okay, so what does that look like? It's just a rect function right here. Okay, move it up a little. And the height is 1 because rect functions have height 1. Okay, I'm not scaling it by anything. And then where do these left and right sides of the rect function come down? Well, it's just when this argument equals plus or minus 1/2. And you can see if I plug in plus or minus t naught over 2 for t, that's exactly when that happens. Okay, so that's how you can get where those points are. All right, so let's find the Fourier transform of this. So what do? Well, we know what the Fourier transform formula is. Fourier transform of a function just looks like this. Okay, so let's plug in for our particular f of t here, which is rect of t over t naught. Okay, so now what can we do? Well, this function is either 1 or 0. If it's 0, then this entire integrand is just 0, and I don't have to integrate over the region where the rect function is 0. I should only integrate over where it's 1, which from the picture you can see is from negative t naught over 2 up to t naught over 2. And in that case, this function is just 1, so I won't write it, and I get e to the negative j omega t dt. Now we can do this integral. So I get 1 over negative j omega, e to the negative j omega t. And I want to evaluate it at these places. Okay, so what can I do? I'm going to write 1 over j omega, and then I'm going to use this negative sign and just plug in the bottom limit first, then subtract the top limit. Okay, so what do I get in that case? I get e to the, when I plug in negative t naught over 2 for t, the negative cancels, and I get e to the j, e to the j omega t naught over 2, minus what I get when I plug in this, which is e to the negative j omega t naught over 2. Okay, now what can we do? Well, you can see that this is starting to look somewhat like a sine function, okay? And we actually are going to try and make this look like a sinc function. So it turns out what we're going to do is multiply by t naught over 2 divided by t naught over 2. And you'll see that this is exactly what we want. Okay, so what am I going to do? I'm going to take this t naught and just write it out front. Okay, so t naught times. Now what's left? Well, I have a 1/2 times a j. Okay, so I'm going to use that to make that sign I was talking about. Okay, divided by 2j, there's that 2 and that j, so now that numerator is looking like a sign. We'll change that in the next step. And then what's all the stuff I have left over? I have this t naught over 2, and I have this omega. Omega t naught over 2. Okay, so now what do I get? I get t naught times, in the numerator, I just get sine, not sinc yet, sine of omega t naught over 2. Okay, omega t naught over 2. That's our formula for sine. E to the jx minus e to the negative jx over 2j is sine of x. Divided by omega t naught over 2. And now look at that. That's sinc. Sine of something divided by that something. That is our sinc function, right? Sine of t divided by t. Okay. And so what I get is just t naught times sinc of omega t naught over 2. Okay, so that is the Fourier transform of that rect function we started with. So let me just summarize that. So here's a Fourier transform pair we've just derived. Rect of that function, or sorry, rect of that argument. This t naught argument just allows you to scale that rect function depending on how wide the rect is you're actually dealing with. So it's pretty useful to have there. Okay, that's a Fourier transform pair with t naught times sinc of omega t naught over 2. Okay, so in a picture, just something to remember. If you have a rect function, of course, you got to make sure all the constants work out. Fourier transform looks like this, a sinc function. Okay, so this is time, and this is frequency. Okay, just a sketch. All right. A little shaky for some reason. There we go. That's better. Okay, so that's a Fourier transform pair we just figured out, but now we want to see what happens when I have a rect and frequency too. So now let's take the inverse Fourier transform of, now I'm going to write down this function and I just know it's going to work out. That's where I get it from. Okay. Of course, you could just do some trial and error and then mess with the result to come to this on your own, but we'll just shoot right for the correct answer. So we're going to look at omega over 2 omega naught. Turns out that the inverse Fourier transform of this is going to be a sinc function. Okay, so that's why I have this argument the way it is. All right, so let's take the inverse Fourier transform. So that means f of t is 1 over 2 pi times the integral of the Fourier transform, e to the j omega t d omega. Okay, we want to see what this function looks like in time. Now we'll plug in rect of omega over 2 omega naught, e to the j omega t d omega. Okay. Now this rect function, when is it 1 and when is it 0? Well, it's 1 whenever this argument is between plus or minus a half. So what do I plug in for omega to make this argument plus or minus a half? Well, clearly plus or minus omega naught. Right? When I plug in minus omega naught, it cancels. I get not minus a half. When I plug in omega naught, I get positive a half. So that rect function is 1 when omega is between negative omega naught and omega naught, and otherwise it's 0, so I don't have to integrate that because I know the integral is just 0. And I'm left with e to the j omega t d omega. So now let's do this integral. So we get 1 over jt, right, because we're integrating d omega, e to the j omega t from negative omega naught to omega naught. There I get 1 over 2 pi, 1 over jt, e to the j. Now I want to plug in for omega, right, because it was d omega. So e to the j omega naught t minus e to the negative j omega naught t. You can probably see where this is going. Okay, let me just change this equation a little bit. So I have 1 over pi t, and then I have e to the j omega naught t minus e to the negative j omega naught t over what's left is 2j. That's good. That's looking like sine. So that is sine of omega naught t over pi t. Okay, so what do I have to do to try and make this look more like a sinc function? Turns out I just multiply by omega naught over omega naught. And what do I get? I get omega naught over pi from that one times sine of omega naught t over omega naught t. And there we go. We got sine of something over that same thing, and that's our sinc function. This is omega naught over pi times sinc of omega naught t. Okay, so what have we shown? We've shown that the Fourier transform of this function is this Rect function. So in order to get the Fourier transform of the sinc by itself, okay, we can just use the fact that the Fourier transform is linear. We saw that in a previous video, and just multiply both sides of this Fourier transform pair by pi omega naught, or pi over omega naught. And you'll see when I write it down, I'll explain it one more time. So the Fourier transform of sinc is pi over omega naught Rect of omega over 2 omega naught. Okay, so what we actually found from this derivation, I'll just write it down real quick so you can see what I mean, was that omega naught over pi times sinc of omega naught t has a Fourier transform Rect of omega over 2 omega naught. But remember, the Fourier transform is linear, so for any one of these pairs that has the scaling property, I can multiply both sides by a constant, and I get another Fourier transform pair. So if I multiply both sides by pi over omega naught, it cancels here, and I'm left with just sinc. And then on the other side, I get that factor. Okay, so we derived this, but then very easy manipulation gives you this. Okay, so that's all that happened there. Okay, so just to draw it in pictures, if I have a sinc in time, of course, you got to make sure you get all the constants right, omega naught t. But if I have generally that picture in time, what it looks like in frequency is a Rect. Okay, so you can see that before, a Rect in time was a sinc in frequency. Here, the sinc in time is a Rect in frequency. You might be wondering, does this hold more generally? That if I have a certain picture in time and a certain picture in frequency, that sort of changing some constants around, because you can see the Fourier transform pairs aren't exactly the same, right? They're not exactly the same in frequency and time, but is there some relationship between them? And there is, and we'll get to that later in the class. It's called duality. Okay, but for now, we'll just leave it at this. And there's just sort of some interesting things you can say about this last Fourier transform property. This last Fourier transform pair, what else does it show? Okay, it actually gives us a way of calculating the integral of the sinc function. Okay, integral of sine omega naught t over omega naught t dt, which is just the integral of the sinc function. You might be wondering, how can we integrate this thing? Well, it turns out this Fourier transform pair gives us a way. So what can we do? Well, this integral of the sinc function in time, what's another way I could write that? Well, if I write out the Fourier transform of that sinc function, it looks like this. So all I'm doing is taking this Fourier transform and just plugging in 0 for omega. So I'm going to evaluate this at omega equals 0. This is just the Fourier transform of sinc of omega naught t, evaluated where omega is 0. Okay, but we know what that Fourier transform is, right? We just found it right up there. We just found it. So this is pi over omega naught, rect of omega over 2 omega naught, evaluated where omega is 0. So I'll just plug in 0. We get rect of 0 over 2 omega naught. Rect of 0 is 1, right? The rect function is just that rect centered at omega equals 0. So when I plug in 0, I just get the value there, which is 1. This is just 1. And so I'm left with pi over omega naught. So pretty cool. So that is the integral of the sinc function. Might be tough to get other ways. This is a pretty cool way to get that result using Fourier transforms. Okay? So that's pretty interesting. And if I draw the sinc function, yeah, I'll start it on a new page. Okay. If I draw the sinc function, let me try and draw it nice and big. Okay, so this is sinc of omega naught t. That means that point right there is 1. And where are these first 0 crossings? Well, they're just the first places that sine of omega naught t equals 0. That's what we said above. Where does sine of omega naught t equals 0? Well, it equals 0 whenever that argument is plus or minus pi. Omega naught t plus or minus pi. That means t is going to be plus or minus pi over omega naught. This is pi over omega naught. This is negative pi over omega naught. Okay, so why would I care about those points? Well, it's pretty interesting. Let me actually draw this a little bit better. That wasn't much better. There we go, it's a little better. It's pretty interesting if we make this triangle. Let me do it in another color. And make that triangle there. What is the area of that red triangle? Well, it's the base times height divided by 2. The base is 2 pi over omega naught times the height is 1 divided by 2 just gives me pi over omega naught. What do you know? That was actually the integral of this entire sine function, or sinc function, sorry. Okay, so the integral of the sinc function we just found above was pi over omega naught. That was what we got up here. And that's also the area of the red triangle. So whenever you have a sinc function and you want to know its integral, you can remember this kind of cool triangle trick. Okay, so it means that the area in this triangle, you might be thinking, wait a second, there's more area right here than that triangle already. But look, the sinc function also goes negative. So when we integrate it, those areas below the t-axis, of course, will count negating. They'll count against the area. You'll be subtracting that area. So it turns out when you add up all the area, when you integrate this sinc curve, it turns out you get exactly the area of that red triangle. So pretty cool. And also we can even look at the special case of omega naught when it equals 1. What do we get? Well, in that case, we get that the integral of sine of t over t, which could be a tough integral to do by other means, but this Fourier transform method is pretty easy, right? You plug in 1 there, you just get pi. Pretty cool. So the integral of just sine of t over t from negative infinity to infinity turns out to be pi. Okay, so pretty interesting. You know, not something we're probably going to use in ECE 45 specifically too much, but it's a pretty cool integral fact that you can get using Fourier transforms. Okay, so that's all I had for this video, and I'll see you in the next one.